Hello everyone and welcome to a Stat 437 lecture video. In today's video, we are going to be discussing transition models for longitudinal data. So to quickly recap where we're at in this course, over the past little while, we've been looking at marginal models and at linear mixed effects models for longitudinal data. And so with marginal models, we sort of focused on taking the ideas of GLMs and applying them to longitudinal data, where we account for within-person correlations by sort of just specifying a correlation pattern matrix and working from there. Then with linear mixed effects models, we modeled explicitly individual effects and population level effects, and doing that allows us to account for correlation within an individual. And so sort of the whole time we've been taking this regression framework approach where we have sort of a mean that we're trying to model or a function of a mean that we're trying to model and specifying some regression models for that. So the idea with transition models is slightly different, and it's best motivated through the idea of categorical data, right? So if we have some categorical longitudinal data, then it might not necessarily be clear how we could go about using the methods that we've talked about so far to model those longitudinally. And so that's sort of where we're going to draw inspiration from in today's lecture. So to recap sort of what I was just saying, we can think of the approaches that we've taken so far, right? So with marginal models, they were models for the population level effects. We specified an overall average and variance, and then we accounted for associations through a correlation structure. Mixed effects models model both population level and individual specific effects. We specified the mean structure, which includes both fixed and random effects. So fixed effects are the population level ones, random effects are at the individual level. So we've specified our mean structure. We specify an underlying distribution. So in the case of continuous data, we saw that specifying that to be normal works out well. And then we accommodate associations through the use of random effects terms, right? So we specify those individual level effects. There's a correlation or a covariance matrix within them, and this sort of is imposing these correlation and variance structures that we had talked about previously. So a natural question to ask then is, how might we be able to handle categorical data? Right? So if you think back to your GLM course, there are actually methods for accounting for categorical data using GLMs, but they're not necessarily the most natural, right? You sort of expand on logistic regression and you can use multiple categories that way. But there's going to be sort of a more natural approach. And so we can take an example here. And so if you imagine the progression of an illness over time, right? Everyone starts off as healthy or without the illness, right? And then oftentimes we'll see people who go from being healthy to being sick and stable, right? So by this, I mean they're sick, but they're not hospitalized for the disease, right? And maybe people move back and forth between these two categories, right? You become sick, you don't need any attention, medical attention, so you become healthy again, and back and forth, right? With something like the flu or, COVID-19, whatever the case may be, you can think about moving between these. Now, some portion of people, once they're sick, become hospitalized, right? They become incredibly sick and they need to see medical attention. And in theory, you might not actually move through both of these at the same time point. Perhaps as soon as you've developed the illness, you could become, the need to go hospitalized again. And then again, once you're hospitalized, you could think about being moved into sick and stable or back to healthy, depending on the case. And then, we might be able to categorize sort of a fourth set of individuals whereby they're not only hospitalized, but they're in the intensive care unit, right? They need very specific medical attention. So you could think about sort of people moving into these categories as well. And so the idea with the longitudinal categorical data is that if we were, say, measuring which category someone was in every single day over a period of time, right? We take a look on day 1, they're healthy. On day 2, maybe they're sick and stable. Day 3, it's the same thing, etc., right? And you can think about this evolving over time. Well, there's sort of a natural structure that we oftentimes talk about in statistics that captures that process exactly. So the question for you is, do you remember stochastic processes, or have you even ever seen them, right? And if so, then thinking about sort of moving between states as we move over time, that's typically the language that we're using to describe a stochastic process, generally speaking, right? So this is the idea, is that a transition model frames longitudinal data as though it's a stochastic process, and then we can use the tools for analyzing stochastic processes to fit models to these data. Right, so to sort of introduce the mathematical notation that we're going to be dealing with, we take this set S here to be some suitable state space. So in the previous example, S is just going to be 1, 2, 3, and 4, where 1 corresponds to healthy, 2 to stable, 3 to hospitalized, and 4 to being in the ICU. But you can think about this as being any sort of discrete categorical state space, right? Then we take time points t, right? And what we're going to be doing is we're going to be thinking about these time points as being discrete time points, and they are equally spaced over time, right? And so then we measure our outcome, yt, which is just going to be some value of s, or inside of that set s, inside of our sample space, and that's the process's value at the current time, at the time t, right? We also define this h set here, so h of t, and that's going to be our history vector. So that's the vector of the process, the whole history of the process up to time t, right? So at the 10th time point, at the 10th day that we're taking a measurement from, this is going to include our baseline measurement, the measurement on the first day, the measurement on the second day, and so forth up to the 9th day, right? So it includes all of the previously observed information, and we call it the history vector. The h is for history. And then we're primarily interested in this quantity given by the probability that at time t, our process is in the state L, conditional on the history, okay? And so you could think about, given some sort of development of this disease over time, what is the probability that the person is healthy at time 10, right? And that's sort of the way that we're going to be thinking about framing this. So it's in this natural, the language of stochastic processes. And so if you remember back to when you were talking about stochastic processes, sort of as, statisticians, the property that we hope to be able to exploit when we're dealing with stochastic processes is this idea of using Markov chains, or using the Markov property, right? And the reason that we care about that is because it makes things a lot easier, a lot nicer to deal with. So what is the Markov property? What is a Markov chain? Well, we call a stochastic process a Markov chain, an nth order Markov chain, if the probability that we're in state L at time t, given our history, only depends on the most recent R states, right? So put differently, if you want to know, say, the probability that we're healthy at time 10, and if we're dealing with a third order Markov chain, instead of requiring all of the information from from time 0 up to time 9, we only require the information at time 9, 8, and 7, because we said it was a third order Markov chain, right? And so the idea here is that we essentially just require a window of information, and then that window slides over time, and as long as we have that window available to us, we can make predictions, right? And so it's a very useful property for simplifying it. Because you can think about, if we don't have this property, right, then as your longitudinal study grows longer and longer, the conditional probabilities you're working with are going to grow more and more complex, right? At time 2, it's not so bad to have to condition on the first few measurements, but at time 200, you don't really want to have to start trying to think about probabilities that depend on 199 previous measurements. So we call a Markov chain an nth order Markov chain if we can drop all of the information except for the most recent R measurements. And so in particular, we're often going to be concerned with a first order Markov chain. So that's taking R equals 1. And in this case, what we have is that the probability that we're in some state at a given time, conditional on our history, only depends on the previous time point, right? And so because of this, what we can say is that if we define these transition probabilities, so I'm calling them PLM of t, that's going to be the probability that we transition from state L into state M at time t. So we're saying at time t minus 1, we're in state L. What is the probability that at time t, we're in state M, right? So probability that y of t equals M, given y of t minus 1 equals L. And if we're dealing with a first order Markov chain, the set of probabilities here entirely defines what the process is, the whole development of that process. Now, we also technically need the baseline distribution, right? So we need to know at time 0, where do people start? But oftentimes we're not actually going to think too much about that, because either we know what that is, or there's some way that we can assume it away, or whatever else the case may be. So we're oftentimes sort of ignoring the baseline distribution. Now, we also might want to call our Markov chain time homogeneous, okay? And time homogeneous just means that these transition probabilities do not depend on the actual time that they're there, right? And so if these transition probabilities from L to M are the same no matter what time we're at, then we can denote them by dropping that t. So they're just PLM, and we call that a time homogeneous, right? So thinking about that sort of rationally, what that means is the probability of going L to M at time 10 is the same as the probability of going L to M at time 2, which is the same as at time 25, right? Doesn't matter when we are, all that matters is we're transitioning from L to M. And that's a really nice property. It's not always going to hold, but when it does, that simplifies matters greatly because we go from needing different transition probabilities at every time step that we care about to just the single set of transition probabilities, right? So that simplifies matters greatly for us. So we can start to think about actually, modeling longitudinal data based on these transition models, based on this framing as a stochastic process. Okay, and so we can sort of define a first order transition model. And so what we're going to be doing there is we're going to assume that we have a first order Markov chain, right? And we want to sort of estimate those probabilities based on a data set, right? So the probabilities that we care about, the parameters that we care about, are going to be this probability that yij is equal to m, given yij minus 1 is equal to L, right? So that's the L to M transition probability. And here, it's occurring at time tj, right? Because we're looking at the jth iteration. And so you can think about, we need this set of probabilities, this set of parameters here, for every single time point that we care about, so for all of those j, and we need them for all different states in our transition, or in our process, all of the categories, right? And so in the case of that simple 4-state example that we had, you can think about there's going to be a probability of moving healthy to stable, there's going to be a probability of moving healthy to hospitalized, probability of moving healthy to the ICU. And then from stable, you might become healthy, you might become hospitalized, you might become in the ICU. And same thing through the other ones, right? And so we're going to need all of those transition probabilities at each different state. Now, fortunately for us, categorical data actually becomes not so terrible to work with in terms of likelihood, right? We don't actually need to specify the distribution in sort of a rigorous form because anytime we're dealing with categorical data, we sort of know what its distribution is going to be. And so the idea is that we can write down the likelihood of those parameters. And the way that we're going to do that is we sort of start off with the product inside of at the baseline time, so at time 1, and then what we're doing is this sort of sequence of data that any individual takes is going to be the probability that they started in whatever baseline state, and then we can multiply that by the probability that they transition to their second observation given their baseline state, and then we can multiply that by the probability that they transitioned to their third state given that they were in the second observed state, and then the fourth given that they were in the third, and so on. And so what we can see is that this is going to be sort of their baseline distribution, which we said was denoted by this pi, right? So it's whatever state they start in. And then we multiply by the sequence from j equals 2 up till whatever our maximum observation is of the transition probabilities from j minus 1 to j, right? So that's the observed data that that individual has. And so multiplying through those whole conditional probabilities ends up giving us the joint probability of observing yi. And then we just multiply that across the whole population here, across I equals 1 to n, and that gives us sort of what we need there. Now again, we'll go through this in sort of more detail in the next lecture. So taking that expression for granted, what we can find is that there's closed formed estimators for the different parameter estimates, the maximum likelihood estimates. So if we're not assuming that it's time homogeneous, then what we get is that the maximum likelihood is going to be the number of L to M transitions at time tj divided by the total number of subjects in L at time j minus 1, right? So we look at everyone that's in state L at time j minus 1, what proportion of those are in state M at the next time? And that's going to be our estimated probability. So it's sort of a nice intuitive sense. If we assume that things are time homogeneous, right, so then the actual time doesn't matter, we take basically the same form, except the numerator, we sum up all of the transitions that have gone from L to M at any point, and then in the denominator, we take all of the people who were ever in state L up till sort of the second last state, right? And we divide that proportion. So it's the total proportion of transitions from L to M over all of the people who are ever in L to begin. Okay, so those are sort of intuitive, nice estimators from them, and we'll see how to get that actual derivation in the next lecture. But there's one sort of major shortcoming of this, right? So we've framed it as a stochastic process. We, talked about the transition probabilities. We saw that we can use maximum likelihood to get those transition probabilities. That's all well and good. But this whole course has sort of been designed around the idea of predicting the longitudinal development on the basis of variates, right? And if we want to test scientific hypotheses, we need to be able to include these different variates. And so how can we go about doing that here? Fortunately for us, there's sort of a natural way. So we can think about defining a logistic transition model or a logistic regression transition model. So if we assume a first order time homogeneous model, and instead of working with arbitrary categorical data, we work with binary data, right? So Yij is going to be either 0 or 1. Now we can define the mean, the conditional mean here, so mu ijc, to be the expected value of Yij given its previous time, which is, of course, the probability that it equals 1 given the previous time, okay? And so this is essentially the transition probability. And if we write this out as a logistic regression model, right, because we're looking at a binary outcome here, we're conditioned on some previous value, we can write this out as the logistic regression where we include alpha 0 as an intercept and alpha 1 times by the previous regression or the previous observation here. Then you can think about the fact that this is sort of going to be capturing all possible transition probabilities, right? Because if at the previous state you were in state 0, right? Well, if you're in state 0 at the previous time, then this term is just going to be a 0, and we get that the logistic regression is going to be alpha 0. So that's the probability that you're in state 1, given you were in state 0 previously, is going to be the x bit of alpha 0, right? And then, of course, the probability that you're in state 0, given you were in 0 previously, is just 1 minus that value, right? Because they have to sum to 1. So now, if you were previously in state 1, well, then the probability that you're in state 1 again is going to be the x bit of alpha 0 plus alpha 1. And then if you want to know the probability that you're in state 0, given you were previously in state 1, it's going to be 1 minus that value, right? And so those 4 different transition probabilities that we care about, where we've assumed that it's time homogeneous and it's a first order model, there's 4 different transition probabilities, and we can get them all from this logistic regression. And then we can do a similar thing for the second order model here. Now there's actually a typo on these slides, and that's because we in fact actually need an interaction term as well. But that's going to be depending on the previous 2 different states. So are you coming from 0, 0 into 1? Are you coming from 0, 1 into 1? Are you coming from 1, 0 into 1? Or are you coming from 1, 1 into 1, right? And so sort of all of those probabilities uniquely characterize it. Again, we would need an alpha 3 term here, and the alpha 3 term is going to have the 2-way interaction, and that's going to capture everything. But so using these logistic regression models, we can sort of reparameterize what we were just talking about with those transition probabilities, where we're basing it on these logistic regression models. And so because we're sort of framing them as these logistic regression models, if we're now interested in the impact of covariates, well, it becomes quite natural just to add in covariate terms, right? So now instead of using alpha 0 and alpha 1, we could use xij transpose times beta, and then xij transpose times alpha, right? And so that's going to be the effects of these covariates, where if we include an intercept term, it's the same thing, right? If xij is just 1, it's the exact same model we were just working with, but we could include whatever covariates we want. And now what you're going to find is that this xij beta term is going to be the transition probabilities when the previous indicator was 0. And then you get xij times by beta plus alpha when the previous indicator was 1, right? And so we're allowing for these transition probabilities to depend on covariates, but we still sort of get all of the ones that we could want out of them, right? So this will allow our transition probabilities to depend on whatever measure factors we want. As we were mentioning, when your previous time point was a 0, then we have the effects being defined by beta. And when the previous time point was 1, the effects are going to be defined by alpha plus beta. right? Because you're going to have a 1 plugged into this term here. And when this term has a 1 plugged into it, we can just factor the xij transpose outside, xij transpose times beta plus alpha. So that gives us the effects there, right? We can also expand this, just like we saw in the previous slides, to allow for even higher order terms, right? And so you don't have to make a first order assumption here. You can make a second order or a third order model, and all that's going to be doing is just adding more and more terms. And the other point here that I don't have written down, but that's sort of important to note, is that this is also going to let us test these hypotheses, right? So we can test whether factors matter. We can test whether a first order Markov chain seems appropriate because the first order model is nested within the second order model and so on, right? So this gives us a really powerful way of framing these transition probabilities. So in practice, if we write down that likelihood expression based on assuming a logistic regression, right? So we write down that the likelihood expression that we were looking at earlier, and we plug in those logistic regression probabilities, what we can find is that it's actually sort of conditional on the baseline distribution. It's exactly the same as what you would find in a standard GLM, right? And what that means is that we can use standard GLM software to estimate this, right? Because the likelihood that we're maximizing, conditional on where you start, is exactly a logistic regression model. And so essentially what we're doing there is we're treating the first set of observations, so the first R observations in an rth order model are going to be treated as fixed or as known. And then from there, we're estimating everything else. Now, there are ways of getting around having to work with this conditional distribution. And typically those are going to result in specifying a baseline distribution into the likelihood. The problem with that is that if you misspecify it, then you end up with a biased likelihood expression. The problem with doing it this way, by dropping those baseline terms, is first, you're not estimating them, right? So we don't get to do any sort of inference on where people are starting. But the other issue, and this is a little bit more subtle, is that we're throwing away some information, and so our estimators are going to be less efficient. But nevertheless, the fact that we can estimate these models using standard logistic regression software is, powerful enough to sort of let us ignore that. And in practice, this is the way that things are going to typically work. And so, pulling this all together, we saw that marginal models and mixed effects models are not going to naturally handle categorical data, at least not sort of in the way that's most natural to think about as a process which is developing, transitioning over time. So instead, we can take that longitudinal process and we can explicitly specify it as a stochastic process and then make an appropriate Markovian assumption, right? So if we assume that it's a Markov model, now what we have is we're observing people over time and we're thinking about them as moving between categories as time goes on. Because of these assumptions, we can use just standard likelihood theory, and that allows us to estimate transition probabilities. And we could use logistic regression to allow for variates to be included inside of those transition probabilities. And so that's sort of the general idea with these transition models for longitudinal data, right? So the basic idea is just that if you think about this as a stochastic process, that gives us a really natural way to parameterize what we might be interested in doing. And then you just have to get a little bit creative for how we're going to include different variates for it. So in the next lecture, we'll go through this again and we'll work through some of that theory and dig into the details of it a little bit. And then following that, we'll see this implemented in R. And when we go to implement it in R, it should be quite familiar because we're using standard GLM software to do that. Now, we saw this sort of only being used for categorical data, and that's where it's going to be certainly most natural to use. And this idea of using logistic regression transitions can actually be expanded when we're not using binary data. But in that case, you just have to sort of use an appropriate model where you're not assuming sort of a binary distribution where you have to assume some sort of multinomial logistic regression. And then from there, you can sort of use the same situation. But for now in this course, if you're going to be fitting them with logistic regression, we're going to be assuming that you sort of have made it binary, right? And so hopefully that all makes sense. Hopefully you've seen stochastic processes enough to sort of feel like this is a natural development. And if not, hopefully it's clear that we can just sort of think about our outcomes as developing over time and being characterized by how likely someone is to move from one category to another. And if we estimate those probabilities, well, then we've sort of estimated everything that we care about. Of course, if you have any questions at all, please ask me over email or however else, and I will see you all in the next lecture.